In this lesson, we'll introduce methods to evaluate limits analytically, which means using algebra. To begin with, we'll have to introduce quite a few properties of limits. And then we can use these properties to evaluate other limits. The first three basic properties that we are going to introduce are listed here. So let's assume b and c are real numbers and n a positive integer. So the first rule says the limit of b when x is approaching c is equal to b. Well, this should make sense geometrically speaking, because when you have a function b, right, which is a constant, say this is y equals b, and when the x is approaching c, and what's the y value approaching? It's going to be b. The second property is the limit of x when x is approaching c is equal to c. Well, geometrically speaking, the function that we have is x, right? So therefore, this is the function y equals c, y equals x. And then when x is approaching c, so what is the function value approaching? It's equal to c because y is equal to x. This is the function. So that both properties make sense geometrically. Pretty intuitive, I would say. Now, if you have watched the video that I created for the formal definition of limits, then proving these two properties will be good exercise for you to practice your skills of using the formal definition of the limit. But here, I'm going to skip the proof. We'll focus on applying those properties. So now let's apply these properties to the following problems, okay? The first one is the limit of 6 when x is approaching 2. Well, according to property number 1, and this is just going to be 6 because this is a constant function, and regardless what your x values is, the y value is always 6. The second one, this is a identity function. When x is approaching -3, the limit will be just equal to -3. Simply do a substitution. Now the next one is a power function, x cubed. When x is approaching 3, then according to the property number 3 here, we just do the substitution, 3 cubed, which is 27. All right, so 3 simple application of those basic properties. Now let's introduce more properties here. These properties are pretty intuitive again. So the first one is the scalar multiple. The limit of b times f of x, where b is a constant, is equal to b times the limit of f of x when x is approaching c. In other words, constant can be pulled out of the limit sign. Again, this would be a good exercise for you to practice proving limits using the formal definition, which I will be skipping in this video. And let's read the next property, the sum and difference. So this property is saying the limit of the sum of two functions is equal to the sum of the limits of these two individual functions. Or similarly, the limit of the difference of these two functions is equal to the difference of the limits of these two individual functions. So kind of like you can distribute the limit symbol, this limit function, into each individual functions. So the product property, the limit of the product is equal to the limit, the product of the limit. And quotient, the limit of the quotient is equal to quotient of the limit as long as the limit of the denominator function is not equal to 0. And the power function is the limit of the power function is equal to the limit of this function and then raised to that power. And radical function, the limits of the nth roots of f of x is equal to nth roots of the limits of f of x. And the composite function, the limits of f of g of x is equal to f of the limits of g of x. Now let's apply these properties to the next question here. So now we have the limits of this function 2x squared minus 1. We want to find the limits when x is approaching 2. This can be very simple, but let's make sure that we know which property we are using. So the first step I would do is I'm going to split this into two limits. So this is equal to the limits of 2x squared minus the limits when x is approaching 2 of 1. Using this property, right? Property number 5 by property number 5. The next step, we are going to pull this constant out. So pull the 2 out of the limits. According to the property number 4 right there, we can move out the constants from the limits. So minus the limits of 1 when x is approaching 2. So this is by property number 4. And then the next, earlier we have, when we have a power function, we can just do the substitution, right? So therefore we are going to do the substitution, and this is constant. So the limits of this guy will be 1. So now we are going to plug in these 2 for this power function. So therefore this will be 2 squared and then minus, and this is constant, so the limits will be equal to 1. This is using the earlier we have previously we have a couple properties. I think it is property 1 and property 3. Okay, so by property 1 and property 3. Now and then we do the algebra. Here's a little observation that I would like you to make. So look at what we begin with and look at what we have now. Do you see that we kind of just plug in the 2 into this expression, right? Into this function, okay? So that's actually what happens. So therefore this is 2 times 2 squared, which is 8. 8 minus 1, which is 7, right? Okay. Well, so the observation is, what I want to emphasize. Basically, what we get is a direct substitution. Now, the next property is the limits of polynomial and rational functions. We assume P and Q are polynomials and C is just a constant. For polynomial function, the limit of this polynomial when x is approaching C, you just directly substitute C into this polynomial function. And that's actually the experience that we have, right? And this can be derived using the previous introduced properties. And for rational function, we can see that the limits of this quotient of these two polynomials, when x is approaching C, you can do the direct substitution, P of C over Q of C, as long as Q of C is not equal to 0. Now, with that, let's take a look at the next example. Here, we have a rational function. So according to the property that we just introduced, so this you can just do a direct substitution, and which is 2 squared plus 2 plus 2, right? A lot of 2's. And in the denominator, 2 plus 1. So this is what it takes, and this is equal to 4 plus 2 plus 2, which is 8, and the bottom is 3, so 8 over 3. And this actually is the function itself. So when x is approaching 2, we can see that this function is continuous, so therefore we can just plug it in. So a direct substitution. So direct substitution for rational functions. Now let's look at the next problem. Earlier we say if we have a rational function, which means a ratio of two polynomials, then we can do direct substitution. Now this is not a polynomial right there. This contains a root. So now let's break it down a little bit here. So this is equal to, we have a property saying that the limits of the ratio is equal to the ratio of the limits, right? So therefore we can apply the limits at x approaching 2, square root of 2x cubed plus 9 plus 3x minus 2. And the bottom is also the limits of x approaching 2, 3x minus 1. And the top, I should probably put parentheses. The top, this is the limits of the first function plus the second function. So therefore, I can actually, according to the sum rule, I can apply. Let me write it on a second line, another new line here. I can actually apply this limit to individual function, right? So plus the limits of the second function over the limits of 3x minus 1. And we have a property that the limits of a root of a function is equal to the root of the limits of the function inside. So we now can apply that. So therefore, we get square root of the limit x approaching 2 of 2x cubed plus 9 plus the limit x approaching 2, 3x minus 2, divided by limit x approaching 2, 3x minus 1. Now, this is a polynomial. We did mention that when you have a polynomial, you just do direct substitution. So this is another polynomial, direct substitution, another polynomial. So therefore, what we have now is actually square root of 2 times 2 cubed plus 9. Okay, so we do direct substitution plus 3 times 2 minus 2. And on the bottom, we have 3 times 2 minus 1. Okay, time to do some observation again and look at what we start with and look at what we have. Basically, applying all those rules, we are actually doing the direct substitution here. Is that right? So, so that's actually not a coincidence. That's what we are going to generalize real soon. So this is going to be, this is 8, this is 16. 16 plus 9 is 25. So square root of 25 gives us 5, right? So therefore, this is going to be 5 plus 6 minus 2. The bottom, we have 6 minus 1. So therefore, the top we have 9, the bottom we have 5, so 9/5. All right, so what I would try to emphasize is, do you see that this is also a direct substitution? So now let's talk about this generalization, a little observation here. You have seen that limits of many algebraic functions can be evaluated by direct substitution. So basically, you just do direct substitution when you see algebraic functions. And what are the algebraic functions? Like the functions that can be created using the basic operations like addition, subtraction, multiplication, division and also the roots, right? The roots. And then when computing limits f of x when x is approaching c, if the function is continuous at c, we'll talk about this more in the next section, next lesson. We simply do the substitution in this function. In other words, the limits of f of x when x is approaching c is equal to f of c. Some such functions include polynomials, rational functions, trigonometric functions, and so then the limit f of x when x is approaching c is always f of c when c is in the domain of these functions. If c is not in the domain, that's another story. Otherwise, you can just do the substitution when you have these kind of functions. Now, therefore, we have the following result for those 6 trigonometric functions. So limit sine of x, when x is approaching c, is just sine c. So just do the direct substitution for all these 6 trigonometric functions. Now, let's apply this result to the next couple problems. So here we do have a trigonometric function, and therefore we just do the direct substitution. This will be sine pi over 4, and this square means the square of the whole thing. So basically that means this. And sine pi over 4, if you remember it correctly, it should be square root of 2 over 2, and then you square it, which is 2 over 4 and 1/2. And the next one, this is actually a product of 2 functions, right? X and cosine x, which is we can use the product rule. We can split that into 2 limits. And then for each, we apply the rule that we have introduced. So limits of the first one, you just do the direct substitution. The next one, do the direct substitution. And cosine pi is -1. So therefore, this is equal to -pi. So seems like direct substitution will be very useful to handle those functions that are continuous, and especially the ones algebraic functions that we already familiar with, including the trigonometric function. Now let's move on to the next topic. Direct substitution may not work all the time. So when it doesn't work, we have to have some strategies to handle that. So now we are going to introduce the first theorem that will be helpful to handle situation like that. The theorem that we are going to introduce is for the functions that agree at all but one point. Here, let c be a real number, and let f of x and g of x be equal for all x except c in an open interval containing c. If the limits of g of x as x approaches c exist, then the limits of f of x also exist, and actually they have the same limit. So now, for instance, how do we actually apply this theorem? Let's take a look at this one. And this is a rational function. And when I have a limits problem, my first attempt is always do the direct substitution. Here it doesn't work because when you plug in 1, do you see the bottom is 1? I mean 1 minus 1, which is 0. The top is 1 minus 1, which is also 0. So 0, 0, we call it indeterminate form. When we say indeterminate form, that means it could happen, anything could happen, just we cannot determine what actually will happen without doing some analysis with it. So this is indeterminate form. When we have indeterminate form, we have to handle that carefully. So now please note that x squared minus 1 over x minus 1, we can actually factor the top, right? And then after that, this can cancel. And then the expression simplifies as x plus 1. Please note that these two are different functions. They're different functions. Why they're different? Because this function x1 is not in its domain, but this function, the domain is all real numbers, right? They're different. However, they are equivalent as long as x is not equal to 1. In other words, so time for us to revisit the previous theorem that we introduced. So do you see that these two functions, call this as f, call this as g, they are equal except at a point 1 when x is 1. So now, according to this theorem, they have the same limits when x is approaching 1. Therefore, even though 1 is not in the domain of this function, we can actually find the limits by finding the limits of this function when x is approaching 1. So for that reason, we actually can go ahead, solve this problem. This is actually equal to limits x approaching 1, x of x plus 1. We did the simplification here. This is equal to that except at this x value 1, right? And then now to evaluate the limits of this guy, we can just do the direct substitution, which gives us 2. Now let's do another exercise here. Okay. My first approach is always do the substitution. You can see that x cannot be 3 in this function. So when you plug in 3, this is 3. When you plug in 3 here, this is 9 minus 6 minus 3, which is 0. So 0 over 0 type again. Now, from previous experience, we can actually try to see if we can factor and simplify. So the top can be factored as x minus 3 times x plus 1. The bottom is x minus 3, and we can cancel that. So therefore, this function and this function, they are equal except at 3. Now we can actually evaluate the limits of this, and this limit should be equal to this limit. So therefore, we can just go ahead do the substitution now, which is 3 plus 1 gives us 4. Okay, so we've seen how this theorem works. And so therefore, when you have situation like that, try to factor to see if you can remove some common factors, and then you can do the direct substitution. Now let's take a look at another type of the problem that requires a different technique. So here, when you, again, first attempt is to do the direct substitution, which won't work, right? You can see this is 0, and on top, when you plug in 0, this is 4 minus 4, which is also 0, and it is an indeterminate form. So here, one of the tricks that we can use is to take advantage of this formula, a minus b times a plus b, which is equal to a squared minus b squared. Take advantage of that. So we are going to multiply the top and bottom by actually the conjugates of this radical expression. So here we basically multiply square root of 16 plus h plus 4 divided by the same thing, basically multiply by 1, but this 1 is the conjugate of this guy over itself. And now, according to the formula, the top becomes square of the first term, which is the square of this guy, the square root will be gone, minus the square of the second term, which is the square of 4. And the bottom, we still have h times square root of 16 plus h, and then plus 4. and 16, negative 16 will be cancel each other. And then you can see that this h and h actually after that you can cancel the h. So therefore you end up with limits h approaching 0, 1 over square root of 16 plus h plus 4, because this h cancel to 1. Now let's try to do the substitution now, and it works. So therefore this is equal to 1 over square root of 16 plus 0 plus 4, which is 1 over 8. Lastly, we are going to introduce the squeeze theorem, a very useful theorem and famous theorem as well. So this theorem says this. Let's zoom out so that we can see the theorem. If h of x is less than or equal to f of x, less than or equal to g of x for all values of x near a, except possibly at a. If the limits of h and g exist when x is approaching c and they're both the same as L, then in other words, this and this limits exist when they both when x is approaching c and they're both equal to L, then this result says the limits of f of x when x is approaching c has to be equal to L. Basically, it's sandwiched by these two functions and force this f to approach L when x is approaching c. Graphically speaking, if we want to show what it is, say suppose this is the first function, which is the g of x, and this is the second function, which is the h of x. And here f of x is in between f of x. And they may or may not define at this point C. So may or may not define. You can see that because f of x is bracketed by g and h, so when when g and h, the limits exist at c, which is equal, then this force f to have the same limits when x is approaching c. So with that, using this theorem, actually we can prove a special trigonometric limit, which is the first. This is the first one. Limits of sine x over x when x is approaching 0. This is actually equal to 1. Okay, and the second limits follow after this result. The limits of 1 minus cosine x over x when x is approaching 0 is actually 0. Let's first apply these results on this problem. Then after that, I'm gonna come back and prove this results. Okay, so we'll move the proof at the end. Now, so let's take a look at how we actually use this result on this problem. Let me zoom in a little bit here. So here, by the observation, this x inside the sine x, and this has to be x. They have to be the same. But now I don't have the same thing. This is 6x. This is x. I cannot pull out the 6. That's a common algebra mistake I see from students. Sine of 6x, this 6 cannot be factored out or pulled out. Now, I do want to make sure that we have the same term here. So it's pretty easy for me to make up this 6 here. So what it takes is I'm going to just create a 6 for the bottom, all right, by multiplying a 1, 6 over 6, so that this is the same as this. And according to a limits property, this 6 can be put out to the outside of the limits sign. So therefore, I have this. And this result is saying when x is approaching 0, then this ratio is equal to 1. Here, this we have 6x inside, but x is the here in the limits, below the limits here. Now, actually, we can say that when x is approaching 0, this guy approaching 0 is equivalent, right? Is equivalent to say 6x approaching 0. So these two things are equivalent. So how about we call this as your u, okay? So think of this as your u, okay? Think of this as your u. And these two will be equivalent. When u is approaching 0, that's equivalent to say x approaching 0. So here, if I let u be 6x, then this will be equivalent. These two will be equivalent. So u approaching 0 sine u over u. That's what we discussed here, right? And this perfectly matches what we just introduced, which is equal to 1. So therefore, this answer will be equal to 6. For the second one, so we can actually rewrite this into using the sine and cosine, right? So tangent 4x is equal to sine 4x over cosine x. By the way, we do have x on the bottom, so don't forget about that. So this is the x. And then we can split this into two limits times the limit x approaching 0, 1 over cosine 4x. And if you just still remember what the trick that we just used, so we actually want to make up this 4, right? So let's multiply by 4 over 4. And the limit of this guy will be 1, okay? So therefore we have 4 times 1, right? Times, and this one, let's try to do the direct substitution when you plug in 0. Cosine 0 is 1, so 1 over 1 is 1. So we have 4 as the answer for this one. Now, finally, I would like to go through the proof of this first result. And this result the proof is pretty nice. So this is what we want to prove. The proof itself is a really nice proof. X approaching 0 sine x over x. It's pretty tricky. It uses some geometry and a little trigonometry there. So suppose this is a unit circle. And then you can think of this x as an angle, because sine x, sine of an angle, right? So therefore, let's call this as x. And because x is approaching 0, you will assume this x will be somewhere near 0, nearby 0. So you would not want to draw your graph like a huge angle. So you want to draw this as a acute angle. Now, take a look at the following shape. So I'm going to form a few shapes. The first one is, by the way, there was something that we need, okay? This angle is x. According to, on a unit circle, this value will be the sine of x. So in other words, the y value will be sine of x. Of course, the x value will be cosine of x, right? Here, this x value will be cosine of x. Now, take a look at this length. This length actually will be tangent of x, because tangent of x will be opposite over the adjacent, because the adjacent is 1. So therefore, this opposite, so I'm going to quickly write something so that you can follow. Tangent x is opposite over the adjacent. And the opposite in this case, that's what we are trying to figure out, right? This opposite is what we want to find. The adjacent is because this is a unit circle, this is 1. So therefore, this length is actually equal to tangent x. That's why we label this tangent x. Now, from here, we can create a inequality. So first of all, take a look at this triangle. Let me continue to zoom in a little bit. So let's look at this triangle with the green edges. Okay, so I just connected these 2 points here, and this triangle. Let's find the area of this triangle. So the area of the first triangle is going to be, so the area of the green triangle is equal to 1/2 times the base. The base is actually 1 times 1 times the height. The height we just mentioned, this is sine x, right? Sine x. And this area is definitely less than this arc area, this sector, the sector that, so if I can take out this sector, the sector right there, okay, because it has a little extra area there. Now, how do you find the area of a sector? The formula is 1/2 times 1/2 r squared theta, where r is the radius, theta is the angle, is the included angle. So in this case, because the radius is 1 and the included angle is x, so basically this area will be 1/2 x. So therefore this has to be true, right? And of course, this sector will be less than or equal to this largest triangle here, that which is this one. And this one, the base is 1, the height is tangent x. So 1/2, the base is 1, the height is tangent x. Now this is when x is greater than or equal to 0, because we draw the angle as a positive angle instead of a negative angle, right? Now, let's say we can actually multiply all sides by 2 so that the 2 will cancel, right? So therefore we have this sine x less than or equal to x less than or equal to tangent x. And they're all positive here, all positive in the first quadrant. So therefore I can, I'm going to divide all 3 parts by sine x. And then again, why we can do that? Because sine x is positive here. So we assume x is actually greater than 0, not equal to 0. Okay, x is greater than 0. Doesn't have to be equal to 0. And then after that, we have 1 less than or equal to sine x over sine of x, less than or equal to, by the way, tangent x is sine over cosine. So therefore, when you sine x, tangent x divided by sine x is equal to 1 over the cosine x. And the result that we want to prove involves sine over x, sine x over x, not the x over sine x. So therefore, we want its reciprocal. And then when you do the reciprocal, just for instance, if you have 1/2 greater than 1/3, right? When you do the reciprocal, like 2 should be less than 3, you have to switch the direction of the inequality sign. So therefore, you do sine x over x less than or equal to cosine x greater than or equal to 1. Now, so all this discussion is based on the assumption x is greater than 0. What if x is less than 0? Now, if x is less than 0, look at here. Sine x, which is odd function, this will be negative. And when x is less than 0, this will be negative. So sine over x still positive, right? So basically, when this x becomes negative, this remains the same. And cosine of cosine x is an even number. So regardless, this positive or negative, cosine x will be equal to cosine of negative x. It's even function, okay? So therefore, the sign really doesn't matter here, and it will remain the same, this inequality. So now we just introduced the squeeze theorem. These three functions, they are equal except at 0, because this 0 is not defined, right? So you can see that when we apply these limits, x is approaching 0 of 1 less than or equal to limit x approaching 0 of sine x over x less than or equal to the limit x approaching 0 cosine of x. And this, when we do the substitution, this is equal to 1. And the limit of this guy, the constant function, is actually equal to 1. Now, therefore, according to the squeeze theorem, this limit has to be 1. Therefore, this result follows. Okay, so this is how we actually prove this famous limit using this little some trick like that. What about the second one? Let's take a look at the second famous result, which is this one. Okay, this one can be done using another strategy. So what we already know is this result. So I try to take advantage of what we have developed, which is sine x over x. And here we have cosine in the numerator. In order for me to create a sine, actually I can take advantage of one of the trigonometric identity. So I'm going to multiply by the conjugates of this guy, right? And then the top I have 1 minus cosine x squared. The bottom is x times 1 plus cosine x. And now after that, let me move my screen. And this is equal to sine x squared, and I can split it into two sine times sine. So therefore I have sine x over x times another one sine x. I'll pair that with 1 plus cosine x. And this is equal to the limit of the product of two functions equal to the product of the limits of these two individual functions. So I'm going to find the limit of this guy, which is 1, times the limit of the second one. Now, time for us to do the substitution, right? So which is sine 0, 1 plus cosine 0. And sine 0 is equal to 0, and cosine 0 is equal to 1. And you can see that the answer, the product, will be equal to 0. So therefore, this is how we prove this one.